For part A, Hooke's law is force spring equals negative kx based on the graph. X is going to be amplitude, starting off with negative amplitude because the block is initially compressed at negative amplitude. Negative amplitude, which a negative times a negative is positive, which leaves me with k amplitude, which is positive, and it's going to be here where force is positive, and then it is released and it goes past the equilibrium to positive A, positive amplitude. It leaves me with negative KA, which is right here. It's going to be linear. For part B, for the XT graph, the block is at negative amplitude, which will start right here, and then it goes past the equilibrium, x being 0, and it goes to positive amplitude, it goes back, and then it goes back to negative amplitude. That is the first cycle. And for the second cycle, it would be the same. For my VT graph, the block initially is compressed at negative amplitude, and at negative amplitude, the velocity at that point is 0. And then it is released going past the equilibrium, where the equilibrium velocity is max. And then it comes to positive amplitude, where velocity at the point is 0. And then it comes back to equilibrium, where the velocity is going now to the left, and it is max. And it stops a full cycle at negative amplitude. For the second cycle, it is the same thing. For my AT graph at negative amplitude, it is going to be acceleration max and also going to be positive, since after it is released, it is going to go to the right. So it starts off here, and after it is released, it goes past the equilibrium, meaning A at that point at the equilibrium is 0. And then at positive amplitude, it is also acceleration max, but after it is compressed again, it is going to go to the left. So right here, back to equilibrium and back to where it started. That is one cycle, and the second cycle is going to be the same thing. For part C, I agree, because the formula for Vmax is negative omega A, and the magnitude is maximum speed, which is just omega A. And I can place my omega with square root k over m. The problem says if I double my a to 2a, my maximum speed will also double. In my Vmax, I have an a and square root k over m. My maximum speed nu also has a and square root k over m. So I can place that with Vmax. And it proves that my maximum speed will also double. For part D, I disagree because the formula for frequency doesn't have an amplitude in it, meaning it isn't dependent on amplitude. The frequency formula is 1 over 2 pi square root k over m, and clearly the formula doesn't have an amplitude because frequency is dependent on K and M. So if the compressed distance is doubled to 2A, the frequency wouldn't quadruple or be even affected or change at all. For part E, I can start off with conservation of energy. And at either amplitude, the energy max would be PE max, which is 1/2 Ka squared. And I could equal that to the energies at any point besides the amplitude, which is PE spring plus KE. KE. And I can break it down to 1/2 Kx squared plus 1/2 MVF squared. And I can move the P spring to the other side, which is 1/2 Ka squared minus 1/2 Kx squared equals 1/2 MVF squared. And 1/2 Ka squared minus 1/2 Kx squared both have a 1/2 in K, which I can group together, which is 1/2 K, and I can subtract the A squared and X squared. So A squared minus X squared parentheses equals 1/2 MVF squared, and the 1/2s they cancel out. And to get VF squared by itself, I will divide both sides by M. And I know that K over M is omega squared, which I can leave as omega squared. So then omega squared parentheses A squared minus X squared parentheses equals VF squared. And to get rid of the square, add the square root, which leaves me with plus minus omega square root A squared minus X squared equals VF. And this proves that the velocity of the block can be calculated using this function. For part F, towards the equilibrium position, there's going to be Fn, Fg. Fn and Fg are going to be the same length. Fk Fk is going to go to the left since the block is being released to the right, and F spring. F spring is going to be shorter than Fn and Fg, and it's going to go to the right since it is left of the equilibrium. And now for the away from the equilibrium position, there's going to be Fn, which for both problems, Fn and Fg are the longest. Fk. And now for away from the equilibrium position, F spring is going to go to the left. F spring is shorter than Fn and Fg, and it is to the left since it is on the right side of the equilibrium. For my scenario number 1, it would be red. My scenario number 2 would be blue. Starting off with scenario number 1, it is initially at negative amplitude, so negative A. It is then released, going past equilibrium, all the way to positive amplitude, and compressed back to equilibrium, and back to negative amplitude. That's for the first cycle. The second cycle would be the same thing. For my second scenario, the amplitude is doubled. So it would be right here, negative 2A and positive 2A. It starts off at negative 2A, released, passing the equilibrium, and to positive 2A, back to equilibrium, and negative 2a. That's for the first cycle, and the second cycle is the same thing. For part H, it asks for a ratio of T3m over Tm, and Tm was before the 2m was dropped on the block of m. So the period formula for just m is 2 pi square root m over k, and on my right side it would be T3m, and the formula is 2 pi square root 3m over k, and I can take out the square root of 3. So I have rad 3 times 2 pi square root m over k, and I can put the T3m over Tm equals rad 3 times 2 pi square root m over k over 2 pi square root m over k. The 2 pi's cancel out and square root m over k's cancel out, leaving me with rad 3, and rad 3 is 1.73, and that is my ratio. For part I agree with the first statement that says amplitude 3m is less than the amplitude of m, because starting off with conservation of momentum, net pi equals net bf m1 vi1 plus m2 vi2 equals m1 plus m2 vf, and it is an elastic equation, completely inelastic, because it says that block 2 immediately sticks to the top of block m, and then m2 vi2 cancel out because it starts at rest. Vmax, because it is Vmax because it occurs at the equilibrium where velocity is max. M1 is just m, m2 is 2m vf, m plus 2m is 3m vf. To get vf by itself, I would have to divide by 3, but first I have to cross out the m's, and then I divide by 3. So I have 1 over 3 Vmax equals Vf. And then to solve for the amplitude, I have to start off with PE max equals KEF. This would be for a amplitude of just m. PE max is 1/2 KA squared equals 1/2 MVF squared. The 1/2 cancel out. To get amplitude by itself, I have to divide both sides by k. A squared is MVF squared over k. To get rid of the square, add the square root. I have A equals square root MVF squared over k. For the amplitude, to solve amplitude for 3m, I would also start off with PE max equals KEF 1/2 KA squared equals 1/2 MVF squared. The 1/2 they cancel out. I have KA squared equals, since it is amplitude for 3m, the mass is 3m, And for VF, I found it earlier, which is 1 over 3 V max. And then I would distribute the square. 3m, that is with 1 over 9 V max square. 3 times 1 over 9 is 3 over 9, which is also 1 over 3. So then I have 1 m V max square over 3. To get amplitude by itself, I divide both sides by k. So over k, and then to get rid of the square, I have the square root on both sides. Amplitude for 3m is square root 1 over 3 m V max over k. And this proves that the amplitude for 3m is 1 over square root 1 over 3 am, because am over here is square root m vf squared over k, which is also over here. And I can just replace that with am. When the second block is dropped, the collision causes the two masses to move together, which increases the total mass to 3m. By using conservation of momentum, the final speed has decreased compared to the original. The spring constant remained unchanged, so it depends on the kinetic energy after the collision. After substituting the new velocity, the amplitude of 3m got smaller. Therefore, the amplitude of 3m is smaller than the amplitude of m.